Okay, let's do an example of finding the equation of a tangent plane to a surface. And we'll do our first example here with the surface x squared over 4 plus y squared over 4 minus z squared equal to 1, which happens to be a hyperboloid of one sheet, sorry. And we'll find the tangent plane at the point 4, 2, 2, just a random point on the surface, part A, and then part B we'll find the angle of inclination of the tangent plane to the xy plane. So this is a graph of the surface, and I think the point is roughly here in the xy z coordinate system, and still trying to figure out how to use this software. So I was working with Mathematica to try to get that image, and I'm not completely happy with the picture, but I'm just going to have to leave it at that for now. I was trying to image it, and yeah, maybe well, that's what I'm going to go with for now. This is the commands that I used to graph it, and this is the equation of the tangent plane. I'll get to how we find that in a second. So yeah, that's what I'm trying to do. Find the equation of that tangent plane. Trying to show how to do that. Alright, so that's the equation of the surface, and that's the point. And first of all, actually it really has to, that point really needs to be on the surface, so that point really needs to satisfy that equation. I really want to check once more to make sure that that's actually going to work. If I plugged in 4, 2, and 2, does this actually satisfy the equation? So that's 16 over 4, and that's 4 over 4. Yeah, okay, right. So just confirming that that point's actually on the surface, and therefore it makes sense to find the equation of the plane tangent to the surface at that point on the surface. Okay. All right, so what's really neat about this is the idea that what we'll do is we'll basically go into 4 dimensions in order to handle this 3-dimensional surface. It's almost like we don't have enough room here in 3-dimensional space, and we need to find some extra space. Let's just call in some architects to just build us a 4-dimensional space here, and we can proceed. Yeah, what I mean is whatever equation you have, you don't technically have to always do this, but I'm going to always do this because it just makes explanation and the general procedure the same and easy to explain. I'm going to bring everything over onto one side, and that's generally the thing that you want to do. It doesn't really technically matter in this case because this is a constant. So, but anyway, let's do this. Let's bring everything over to one side. So we'll go x squared over 4. You can always do this, and sometimes, most of the time, you have to do this. Minus 1 equal to 0. So if you take whatever equation with whatever variables, it doesn't matter how many, but generally we'll have 3 variables when we do this kind of thing. We have 3 variables, bring everything over to one side, and then say this is a function of 3 variables, and define this to be big F of x, y, and z. And this is where my 4-dimensional space comes in, because what is the function equal if you plug in x, y, and z? Well, it would equal some other value that you might call w, and in this instance, this function is equal to 0. So this means that the function is equal to 0 constantly. And so what we're doing is, imagine that in a 4-dimensional space, if you plot all the points in 3-dimensional space where the function is constantly 0, you're creating a level surface for w. And it's called a level surface, and sort of the way that I interpret the meaning of level is in the sense that you've got all the points where you're at a constant level, in this case a constant level of 0, where w equals 0. You're plotting in 3-dimensional space with this surface the level surface for w, the surface where w is equal to this constant level of 0, right? In 3-dimensional space where w is the same value is a 3-dimensional surface. This just a fascinating, beautiful idea. And we use this general principle that gradients, so the gradient of f is a vector, it will be perpendicular to the level surface at any point on the level surface. And in fact, you might use the word normal because it's a little more general than just saying perpendicular. So it's normal to level surfaces. So the gradient of f, this big capital F, is normal to level surfaces of f at any point on the level surface, and in particular the point that we're interested in, 4, 2, 2, is one point on that level surface. So, meaning that we could use the gradient as the normal vector to define the plane that we'll call the tangent plane. So with that equation and the definition that f, x, y, z is this multivariable function, then we'll do the gradient of f, which is each of the partials times each of the unit vectors. So in this case, it'll be a partial of f with respect to x times the unit vector I, the partial of f with respect to y times the unit vector j, and the partial with respect to z times the unit vector k. Partial of f with respect to x would be 1/2 x. And that's it, because the derivative with respect to x for the rest of these terms is just going to go to 0. Derivative with respect to y, that's going to be 1/2 y. And all the other terms go to 0. When you take a derivative, this x squared over 4 with respect to y, it's 0. This is going to turn to 0. Of course, that's constant, going to turn to 0. So that's all we get for the partial with respect to y. And then the partial with respect to z, each of these are plus, but this is a minus, so we could just say minus 2z, because going through with the derivative with respect to z, this goes 0, 0, minus 2z, unit vector k, and of course 0 there. So that's the gradient, and it produces a vector in three-dimensional space that would be perpendicular to the surface, or you could say normal to the surface. So this vector, this gradient at the point 4, 2, 2 is the gradient. When you plug in 4, you're going to get 1/2 of 4, and that's 2. 1/2 of 2, and that's 1. And minus 1 for the k component. So if I plug in 4, I get 2. And if I plug in 2, I get 1. And if I plug in 2 again, that's a minus 4 here. And yep, that would have been a mistake. All right, so now we got 2, 1, negative 4 for our normal vector. It isn't a unit vector. It's just a vector that is normal to the tangent plane, and therefore, normal to the surface, and therefore will be normal and perpendicular to the tangent plane. It will be the direction vector for the tangent plane. Okay, moving on. So what we do here is we want to find the equation of the plane that has this as the normal, which means that I'll use a normal vector that is components A, B, C that sort of give direction for the plane, and I will use that as the A component, that's the B component, there's the C component in this equation of a plane at this particular point. So I've got sort of the direction for the orientation, you could say, for the plane, and a particular point for the plane. The x naught, y naught, z naught is one point that I know is on the plane, and that's this 4, 2, 2. Okay. I'll say it because it's right here, a chance to say that, where this equation of the plane comes from is if you think about x, y, z as some arbitrary point on the plane, and the x naught, y naught, z naught is some fixed point on the plane, imagine the vector from x naught, y naught, z naught to the x, y, z. That would have components that are right here. And then imagine the normal that has these components a, b, c. If you did a dot product with those two vectors, it has to be 0. That's where this equation of the plane comes from. It's all the vectors who have terminal point x, y, z from the initial point x naught, y naught, z naught that are perpendicular to the normal vector n. Voila. Okay, so moving on. I want to plug in the A is 2, x minus the x naught is 4, the B is 1. So I've got y minus the y naught is 2 right here, and then I've got negative 4 times z minus the z naught. The z naught is 2. And there's so many things to keep track of there. So then distribute and simplify. And there's the equation of the plane. Looking back at a picture of that, I have another picture of it, which I'm still not completely satisfied, but that's got to be it. I'm using those equations, and I don't love the picture, and I can't make it any better. So it's tangent to a point on the surface that seems to be right around in there. So now let's find the angle of inclination of that tangent plane to the xy plane. So I'll say theta is that angle of inclination that I'm looking for to the xy plane, and it'll be the angle between, it'll just be the angle between the normal that I found to the plane and the unit vector k, because the unit vector k is normal to the xy plane, and so it's the angle between those two vectors that is what's called the angle of inclination. It's the angle between the planes. It's the angle between the tangent plane and the xy plane. It's exactly the same as the angle between these two vectors. So we can find angles between vectors this way. We'll say that the dot product, so we'll just use that the dot product of n and k is the magnitude of n and the magnitude of k times the cosine of the angle between those two vectors, and solving for theta. This would generally find the angle between any two vectors, but if you want the angle between two planes, you only need an angle up to 90 degrees. And so for that reason, you can take an absolute value. For the angle between planes, the absolute value is included because the maximum that it ever could be is 90 degrees. As soon as you pass 90 degrees as an angle between two planes, then you could once again measure on the other side of the angle between the planes. You could just measure again 0 to 90. So this is always part of the angle between planes. Of course, k is the unit vector. In this example, the n is 2, 1, negative 4. N is 2, 1, negative 4. Don't forget the absolute value. Magnitude of n times the magnitude of k, which of course is just 1. So 0 plus 0 plus negative 4. So the absolute value does play a role here. 4 plus 1, that's 5, plus another 16, that's 21. So our cosine inverse of 4 over square root 21. And in a situation like this, it makes more sense to put it in degrees. It's a little bit easier to visualize, usually, to visualize degrees. So I come up with about 29.2 degrees as the angle relative to the xy plane. I know it doesn't really look like 29 degrees, but that's what I get. Yeah, okay, maybe 29 degrees. That's what we get. All right, so that angle from the xy plane up to this plane, that angle there is about 29 degrees. All right, let's do one more example here. Find the equation of the tangent plane to the surface given by x equal v squared sine 2 theta over 9.8 at the point 20, pi over 4, and 40.8. Now, in this coordinate system, I've got a function here of two variables, v and theta. It actually gives me the range of a projectile with initial speed or velocity v and initial launch angle theta when it's launched from the ground. How far will it go? So I'm going to take this coordinate system as here is a value for the velocity. This is a value for the initial launch angle, and this is the output of the function, which is the range of the projectile. So I've graphed that surface, and I've graphed the actual tangent plane at that point on the surface. So here I have an axis for the speed, another axis for the launch angle, and then the corresponding range that you get with that combination is graphed as this surface. You can see this around pi over 4 is where you get the biggest amount of range for a given fixed velocity. You get the most range, the furthest range at 45 degrees, or pi over 4 as your initial launch angle. So let's take that point right there and find the equation of this tangent plane. So the way we'll do that is we'll take this equation and rewrite it so that we move all of the terms and everything in the equation. You can do this with any equation, move everything over to one side. The reason to do that is so that you get it equal to some constant, and it would always be equal to 0 if you do that. And the purpose of doing that is to create another function that is one variable more than you had before, that represents all the variables of the given equation as it was originally, but all now together, that you can actually define that as a new function, capital F. So that's what I'll do. I'll say this is all capital F. It's a function of the velocity and the angle and also the x value that represented the range of the projectile. All of those are the inputs for this capital F function, and it produces a value that you could call W, which actually means I have 4 variables now, and I've constructed something now that's in 4-dimensional space. But all the points where W is 0 is a level surface. It's the surface of points in 3-dimensional space where the W is a constant 0. So that's called the level surface, right? All the points in 3D space where W equals 0 is a level surface of F. That level surface is the surface that was given. So the given surface is one level surface of this function W. Because the given surface that we have is a level surface of W, what we'll do is we'll find the gradient of W, or the gradient of big F, and that vector is a vector in 3-dimensional space that would be perpendicular to any level surface of W. So that's what I'm doing here, is I'm finding the partial derivatives of F with respect to each of these variables. So the partial derivative with respect to X is 1, because when I take a derivative with respect to X, I treat every other variable as a constant. So V and theta all considered to be fixed. Derivative with respect to X is just 1. When I take a derivative with respect to theta, now X is a constant and V is a constant. And so when you take a derivative of the X, it just goes to 0 here, and I get the negative V squared over 9.8. That's a constant, times the derivative of sine 2 theta with respect to theta. So the derivative is only with respect to theta. That's why you can see this negative V squared over 9.8 becoming a constant factor. The derivative of sine 2 theta, that's cosine 2 theta, times a 2 because of the chain rule. And then simplifying the 2 and the 9.8, I get this as the partial derivative of capital F with respect to theta. And there's one more variable there, that's V. So taking a derivative of this function F with respect to V, X is a constant, it goes away in the derivative. When I take a derivative with respect to V, I'm looking at the sine 2 theta over 9.8 as a constant. And just taking a derivative with respect to V, I get negative 2 times V times that constant factor. And simplifying that, I get negative V sine 2 theta over 4.9. Now let's put all that together to find the gradient. It's the gradient that will be the normal to the surface, right? Because gradients are always perpendicular or normal to level surfaces at points which are on the level surface. So I'll use this particular point and find the gradient at that particular point. So I'm plugging that point into the gradient to use that as the normal vector. Now I need to pay attention. You know, I didn't pick the easiest example, but part of why I'm doing it is because I want to. So you know, the fact that the variables are kind of peculiar is really means that we've got to pay close attention to what we're doing. This first component can't be x, which was what I would have done by habit, but it actually has to be. If I'm going to write it as a vector with these components, I actually have to put the components in the right order if I don't identify I, j's, and k's here. So yeah, I'm going to put it in the right order. So the partial of f with respect to v, when v is 20, is negative 20 sine 2 times pi over 4 over 4.9. Now I'm trying to figure out the partial with respect to theta, plug that in next because theta is my second component. So partial with respect to theta at this particular point. And finally the partial with respect to x at this particular point is just going to be 1. That might have fit the way it was, but this is sine of 2 times pi over 4, so that's the sine of pi over 4, 20 over negative 4.9, negative 20 divided by 4.9. This is the cosine of 2 times pi over 4, so that's the cosine of pi over 2, and the cosine of pi over 2 is 0, so this whole thing goes to 0, and this is 1. These are the components that I need for my normal vector. I could have written it just like, maybe could have said, you know, the partial with respect to x is 1, the partial with respect to theta, that's 0, and the partial with respect to v, that's the one that came out negative 4.08. And it's here that, now at this point, when it comes to just writing the equation of the plane, I can just take, it doesn't really matter what order I put the terms, as long as I put partial with respect to x times that change in x. So like it doesn't matter what order, so I'll just emphasize that I could do 1 times x minus the actual x value, which was 40.8, plus, now if I, let's say I do the theta, so of course that's 0, so the theta minus what's the actual angle at that point, pi over 4. So this is my point on the surface, and this is the normal vector. So then the next one is the partial with respect to v, that's a negative 4.08, and then it's got to be v minus the v naught, which was 20. Right, so that's the form of the equation of the tangent plane. It doesn't really matter which of those terms that I wrote first or what order I put them. I just have to have x go with x and theta with theta and v with the v. Another thing that I can say again, how it's often a mistake that people make on exams here is that they leave these partials with variables. And if this is going to be a plane, you've got to have a constant normal vector. So we've got to get these partials evaluated to actually get constants, to actually get the equation of the plane. The plane has to be linear in each of the variables. Well, in this case, 1 times x minus 40.8 is x minus 40.8. And this is just 0. And then we've got negative 4.08 v plus the 4.08 times 20, 81.6 positive, and then if you combine 81.6 minus 40.8, you get positive 40.8. So that's it. That's the equation of the tangent plane. Maybe you could see now how I could see this equation of the plane also as a line here in the xv plane. So if you graph that equation in an xv plane, it would create this line. But then, since there's no theta, the plane actually runs parallel to this theta axis. So this is meaning that there's no change in the x value as you change theta. Let's just say that changing theta doesn't have any effect on the x value, doesn't have any effect on the v either, but points on that plane, you could have any theta and you still have, you continue to have points along that plane. Okay, I think I'll stop there. That was the end of the video. Hopefully it was interesting and helpful.